Okay, now we're going to look at this really interesting matrix called an elementary matrix. Here's the definition. An elementary matrix is one row operation on the identity matrix. And this matrix is useful because the product of the elementary matrix and a matrix A is that same operation applied to A. Let me show you with an example. So let's look at the elementary matrix that involves a row interchange on a 3x3 identity matrix. So we have the standard identity matrix, which is ones on the diagonal, and we switched row 1 and row 2, and this is our identity matrix. We call it E1. Let's look at another identity matrix, or elementary matrix, excuse me, and that is going to be 1 0 0 2 1 0 0 0 1. And this elementary matrix is the identity matrix with the row operation row replacement 2 times row 1 plus row 2 is the new row 2. So this encodes that row operation. Okay, so now let's just make up an A. We'll do 1 2 3 4 5 6 7 8 9. And we'll justify this claim that the product E and A is going to do this same row operation to A. So let's consider E1 times A. So 0 1 0 1 0 0 0 0 1 times 1 2 3 4 5 6 7 8 9. So first row, first column, that's going to be a 4. First row, second column, that's going to be a 5. First row, last column, that's going to be a 6. Second row, first column, that's going to be a 1. And you can see that row is going to be 1, 2, 3. And then the last row and all the columns is going to result in 7, 8, 9. So you can see we did this row operation. We swapped row 1 and row 2 in the A matrix. Let's do the second one. This one's a little more algebra. So we have 1 0 0 2 1 0 0 0 1, and we're going to multiply that matrix and 1 2 3 4 5 6 7 8 9. So you can see that the one row is going to just produce the 1 2 3 row. So the first row is unchanged, and then this 2 1 0, when you multiply by the first row, or first column, excuse me, you're going to get 2 plus 4, which is 6. Then when you do this second row, second column, you're going to get 4 plus 5, which is 9, and then 6 plus 6, which is 12. And then the last row in each column is going to produce the last element in each of those columns. And you can see that if we look at this matrix and we take 2 times the top row and add it to the second row, we get this result. So this is indeed 2 times row 1 plus row 2 is my new row 2 applied to the matrix A. Let's look at a theorem. This theorem is an if and only if statement. It says A is invertible if and only if A is row equivalent to the identity matrix. And furthermore, the row operations that turn A into the identity matrix when applied to the identity matrix turn into A inverse. So this statement is a if and only if statement, so the arrow goes both directions. And so when we go through the proof here, we're going to prove both directions. I.e., we're going to start with A is invertible and show that it proves that A is row equivalent to the identity. And then we'll start with A is row equivalent to the identity and show that A must be invertible. So we'll start with this direction. So we'll start with A is invertible. If A is invertible, then AX equals B has a solution for every B. And this is true because the solution is the inverse times B. This is a theorem. So A is invertible implies this statement. If ax equals b has a solution for every b, then A has a pivot in every row. This is a theorem. So if there's a pivot in every row and there's n rows, we're assuming A is square because it's invertible and we're only working with square matrices here. If you have a pivot in every row, it's going to have a pivot in every column. And if you have a pivot in every row and every column, then you're going to be row equivalent to the identity matrix. All right, so we started with the left-hand side and we showed that the right-hand side follows. Now we'll go the other direction. So we'll start with the right-hand side. A is row equivalent to the identity. And we're going to use these elementary matrices to encode the row operations. So if A is row equivalent to the identity, this means there's a set of elementary matrices, we'll call them E1 through En, that when applied to A, get me the identity. So these are the row operations represented as elementary matrices. And let's just say, let's say there's n of them. Actually, since we use n to denote how many rows and columns we have, let's make this p to distinguish them. So there's p of these. And now what's cool is that this sequence, if we multiply all that out, this is going to be our A inverse. We'll call A inverse EP through E1, the product of those elementary matrices. And we're done. All right, so let's do an example. Let's augment this matrix A with the identity matrix and then row reduce to find A inverse. And I'll explain how this works in a second, why we're doing this. So we're going to put the identity matrix here. We're going to row reduce. And I'll leave it to you to do the calculations or to throw it in your calculator. So if we row reduce, we'll get 1, 0, 0, 1. And then the augmented part will become 9, 7, 9, 4, 5. And now we're going to notice something interesting. This is A, and this is the identity. And when we row reduce it, this becomes the identity. And I claim that this becomes A inverse. And let me explain why. So we'll do this a little more generally. So let's say we have A augment I, and we apply a bunch of row operations. So EP through E1 times A, and if we do those row operations on the first part of the matrix, we're going to be doing those row operations on the second part. So they're going to all hit I. That's going to make this first part I. Well, what happens to the second part? What happens to the augmented part? Well, if we go up here, we see that the inverse is exactly EP through E1. So EP through E1 times the identity, that's just the inverse. So this augmented part will become the inverse. And that's what the theorem is saying up here. It says, when the row operations that turn A to I are applied to I, they turn it to A inverse. So this is a very powerful technique. We have a formula for finding inverses for 2x2 matrices, so we can do this by hand another way. But if we're working with 3x3, the formula is much more complicated, and it's much easier to just use this method. You augment A with the identity. If it's a 3x3, you'd have a 3x3 identity here, and then you row reduce it. You'll get the identity in the first part, and you'll get the inverse in the second part. And you can check your work by just multiplying A and A inverse and seeing that when you multiply those two things, it produces the identity.